Kia ora, welcome everyone. Welcome to our first speaker session of the conference. My name is Olivia Angelin-Bonnet and I'm a statistician at Plant and Food Research, and I will be sharing this first session. So I'm really excited about that. We had an excellent plenary speaker just before, and we're gonna hear some very interesting talk in the coming session. As a quick reminder, as you're listening to all of the talks, please don't hesitate to pop any questions that you might have in the live Q&A, and we will do our best to address all of the questions at the end of each talk. Without further ado, I think we can get started with our first speaker. So please welcome with me Petra Mühlner, who's the Science and Data Director at EPI Interactive, and who's going to talk to us about from risk models to dashboards, case study in empowering research. Thank you very much, Petra.
Thanks, Olivia, for the introduction and for hosting these sessions. Yeah, I'd like to talk to you about something that I'm very passionate about, which is like empowering research. So I'm an epidemiologist and I spend a long time in academia, you know, like trying to model risks and make inferences from data to inform health and animal health decision making. And before I dive into and show you a little bit like what we've done and what I mean with this, I really need to thank all the amazing people that, you know, our team at EPI Interactive had the opportunity to work with over the last almost 15 years, you know, and without them, all the cool stuff I'm able to show you today would not have been possible. So thanks, big shout out. Very grateful to work with these amazing people. So, you know, a big thing for us is when we try and develop, you know, software solutions is always that user expectations are huge, right? People are impatient, you know, it has to be perfect. It has to look perfect on mobile, it has to be intuitive and fast. And I think this can be really hard to meet. And I often get that when we release a tool that people go like, it's not working. But, well, it actually does. So, you know, very impatient users that we got to cater for to make our research shine. And then we also have, when we look at like, when we have a complex analysis or research outputs that we want to share, like so many different tools now, you know, at our hands that different organizations can use. And so we gave this a little bit of thought. And I think there's pretty much a little bit like different levels of what the user needs. So a lot of the business users, you know, like analysts, they like to work with more point and click and out of the box tools. And the more you go into the quantitative space or then into the programmer space, the tools become more advanced. And I think where we operate is really where we use like highly customized scripted tool, you know, that are based on R and Python, like open source software. And that lines up really well because, you know, that is often used in research for the analysis to begin with. Hang on. Here you go. So when we work in R and doing our analysis in R, as many of you will do, we have a natural transitions from R to the R Shiny package that allows us to publish our outputs on the web. So this is just an example of an R Shiny app, and I'll show you this particular app in a little bit more detail in a moment. And what I really like about R Shiny is that it allows us to custom themes. Like, as I said, we have very impatient users, but here we can extend it with common web technologies and then, you know, make it really pretty, make it so it really fits the conventions of a field. And the fun bit is it's also free, it's accessible and easy to get started. So in that way, it allows us to help students, you know, with their projects and develop simple apps, to also develop highly complex apps, you know, that have a lot of users and that have to meet a lot of like more organizational and stakeholder expectations. And a lot of you will already know this, right? We've got like an ecosystem of a Shiny where we have this web front end and then we've got the back end and a variety of data connectors. So quite a lot of opportunity to play with. And, when we talk a little bit about users and we talk about research software, a feature that we found a lot of people really, really like is self-service PDF reporting. Organizations or research projects, there is an expectations, that there is reporting. People can access results, as they see fit. And so the ability to actually integrate like downloadable PDF reports, into dashboards is very, very popular. And also at the same time, the mobile support, especially for apps that people access in the field or on the go. This is also something I feel like we really need to increasingly meet. But what I really want to do now is take you a little bit on a wild goose chase into like just some examples, what I mean was what I just shared, what do we actually do when I talk about that stuff. So I'm just going to show you a couple of examples how we've used some research outputs, that were highly complex and specific and connected them with an audience into easy to digest outputs. So the first app I want to show you is an app we called Epidemics. For those of you who work with infectious diseases, what it does, it aims, you can recognize the typical curve here of the SIR models where we look at like susceptible, infectious and recovered individuals. So the app actually allows people to give an interface of these complex models and also shows like the different, how influential different parameters are. So it's a very, very complex mathematical models, and then people can exploit. So this app is used a lot in teaching. We developed it in collaboration with the City University of Hong Kong and the Royal Veterinary College in the UK. And users can do things like look at different infection states, and also include control efforts like vaccinations. There's a lot of different models in there. Like as you can see here, there's also on the bottom a network model. So it's free to access for everyone to play with. But I'm just quickly want to show you a little bit of what it does. So here you go. So this is pretty much the app now. We have a plus in the base version now, but this is like the base version now where we just added an ability to for people to generate parameters and have AI suggest some parameters. This is, of course, really experimental, but I wanted to show this here as well because it just shows the many, many things we can do and integrate in an app like this. You can see there's lots of like interactive visualizations where users can explore the output. They can download data. There's data tables. And we've also included some functions where people can compare the parameters. And this was really like to make infectious disease models better understood and linked with policy and decision making so they can be used wisely to support disease control. So, for example, here we allow users to investigate, the effect the daily number of effective contact rate can have of different infection stages. So there's lots of interactivity and kind of trying to allow people to play with some, quite complex analytics. And then we also have some disease-specific models in here. So this would be for African swine fever. We also have COVID and avian influenza. And again, here it is about showing people the importance of, early detection and interventions to control these animal diseases. Again, highly customized outputs, that match like the need, the research, or like the practical situation the research, aims to address. And then hang on, this is me. Interestingly here, what we also have in this one is certain scenario exercises, because I want to show this here because often in some of the software we develop, education plays actually a huge part. So here we actually have embedded a scenario analysis into the application to actually show users or students, how they can apply, what the app does and apply it to a problem. And then interestingly, because this is actually used in an international context, here we have a multilingual functionality. So it is being translated. We crowdsource those translations, from different people who kindly translate it for us. So it can be widely used and is not just accessible to English-speaking users. So the second app I'd like to show you is an app called OpenFMD. So FMD, for those who are unaware of that, is foot and mouth disease virus. It's one of the most important livestock diseases globally. It's also a very important disease for New Zealand because New Zealand is free, and actually getting FMD would result in significant trade restrictions. So it's a disease there has a lot of interest, affects the livelihood of people in many countries, and for which, we have global surveillance measures in place and also a lot of genomic data. And so for this project, we partnered up with the Pirbright Institute in the UK, which is the World Reference Lab for FMD virus. So they have quite a big database of the virus. And, so we developed a big platform for them with funding from the European Commission and the Food and Agricultural Organization of the United Nations. And what we're doing here is we have like this research database of all around the world, and we're allowing people here through various tools to explore the data. So this is where people can upload their sequences and compare them with sequences in the database, and then create reports from that, and use those similarities of what they find to, design control efforts. So then they get like this report. So this is really about making this type of specialist analysis accessible. We have the same like on a spatial level. So this is about the ability to explore, the data on the, on the website. We can put like things like animal density on top of it, or stages in the controlled pathways. So there's a lot of detail. It makes it wide open and accessible. People can look at the data, download the data, use it for research. So the platform is called OpenFMD, really to support that global collaboration and surveillance on this important disease. And finally, we also have a vaccine matching tools that allows countries to look at the risk. So this is a research project, where people developed a risk assessment tool that allows people to look at different lineages and the vaccine coverage from different vaccine against strains, and then look at the situation and then identify which is actually the most suited vaccine, for their specific risk profile. So this is really, I really like this because it's really complex research. Your head would spin if you read the paper, but the interface kind of makes it like accessible and actually usable for those people that have to decide which vaccine strains to pick. So I'd like to show you this tool as well, because this is more like qualitative research from the University of Chicago, the Center of Democracy. So they had a really, really nice data set and analysis where they looked at democratic erosions, across the globe, and they looked at democratic performance, political rhetoric, and referendums to get like a feel for democratic erosion. So there's lots of tools we did there, like uploading a speech. So this is quite nice because, it's a bit less quantitative than, for example, the genomic tools we showed you. And so it was a little bit of a challenge, how can we visualize the data? How can we look here at, compare quite a longitudinal data set. We could look at different countries, going back in time and see, for example, different indexes the researchers there calculated to assess performance. And then here, this is also exploring the sentiment, in speeches from different politicians, so you can see how they speak about minorities, for example. So very nice. And then I just gonna show you, flick through a couple of tools that we've done. I wanted to give you the spectrum of like all the different things that's possible when you work with this highly customized tool. So this is a climate matching tool that we did with funding from MPI, with the analysis and the models being developed by researchers from Ag Research, actually. So this is all freely available online. There's teaching tools, that we've done with Shiny for the University of Melbourne here, for example, that tries and shows student, how, like in a really hands-on way, how to calculate epidemiological measures of associations. We worked with the University of Minnesota on lab data, supported the WHO on their antimicrobial resistance data and surveillance program. There's cancer, so it's really just beautiful how you can plug and play and create something really unique that suits the users. And here's a tool, the Aquatic Invasive Species Explorer, that my colleague Nick will show you in a little bit more detail this afternoon. And yeah, so I just want to wrap up with this. I hope, there's a bit of a fun ride of, the possibilities we have nowadays to connect research with an audience. And so in our experience, the scale is often a problem. We have great ideas in research, but scaling that up into a piece of software effectively can be challenging. We need a data pipeline, we need a fit for purpose interface, and we need to cater, depending on the app, for quite large user numbers. And so this is kind of something we've learned to fill that gap, to work with researchers to scale up and use software engineering principles and have this deep integration of disciplines to help make tools like the ones presented possible. So all the tools that I showed you today, you can just hop on our website if you want to have a play with them and have a look if they apply to your work. Flick us a line if you have any questions. And we're in Wellington in New Zealand. We collaborate with a lot of research groups. So yeah, stay in touch, reach out. We'd love to hear about what others are doing in this space, which is, why we're excited to join the conference. And also, if you want to do more with Ashani, we do run a masterclass series where we often have research groups attending. Yeah, and thank you very much. So I'm looking forward to your questions.
Thank you very much, Petra. That was a very interesting talk and a lot of pretty visualizations.
Yeah.
So we have time for a couple of questions. So again, please don't hesitate to put questions in the Q&A. We're going to start with a question by Wolfgang, who is asking, how is the AI parameter generator integrated in your in the first application that you showed? So do you run your own LLM backend for this?
Yeah, so for this one, if you want all the technical details, Nick, our software engineer, will speak later. He can give you the whole details, but we use ChatGPT for that one. So we tried and do, this is a bit experimental, something we wanted to do as part of the research we do with the City University of Hong Kong. But so we kind of like, first of all, I think the idea was to see, is this technically feasible and how can we integrate it in Ashani? And then we've tried different, validation strategies for the models and things like that. So, it's interesting. And but I think in terms of Ashani and large language models or any machine learning, that's the beauty of it as well. We can easily kind of integrate those in the apps. Yeah.
Thank you. And while we wait to see if anyone else has questions in the Q&A, I just have a quick question around how do you go about developing these very complex apps that look very beautiful and very simple, but as you said, the back end of that is very complex research. So do you have kind of a feedback with the researchers? Do you have beta users? How does that work?
Yeah, that's a really good question. So I think what we try and do, we make it really research centric. So we try and, because also not all of these topics, they're kind of quite a diverse set of research topic. So we're really trying to understand, who the researchers want to connect with, and what type of stakeholders they're talking to. And then we go through a very detailed creative process, where we kind of like draw up, through our design team, how the app could look like, what functionality it has, how can we simplify the interface so it is user-friendly. And then it is a highly collaborative project. And then we test the app and, we might have like stakeholder groups. And I think that's really important to really deeply integrate, the research and the information technology, that there is a lot of collaboration and conversation going on. Yeah.
Awesome. Thank you very much. I don't see any more question in the live Q&A, but please feel free, if anyone thinks about something else that they want to ask Petra, feel free to keep adding, and maybe if we have time, we can go back to the questions at the end. So thank you again very much, Petra.
You're very welcome.
We will move on to the next speaker. So our next speaker is Alexander Plitzer, who is an HPC research engineer at NIWA, and he's going to talk about plugging memory leaks in a scientific code. So again, Alexander, thank you very much for joining, and the floor is yours.
Well, thanks, Olivia. Thanks, Petra. Really interesting talk. And this talk is called "Plugging Memory Leaks in a Scientific Code," but it could also be entitled, "A Day in the Life of a Research Software Engineer." And it shows, how varied basically the research software engineering world is between Petra and what we're doing, with some similarities, nevertheless. So this is work. So my name is Alex, and we worked essentially with Chris Scott, who's also attached to NZRSE, but he's working for the University of Auckland. I'm working at NIWA, and here it's really a collaboration between NZRSE and NIWA. Through a consultancy service that we're offering to all our users. So something that, if you want to work with us, you can contact us. I put my email address here on the first page. So if you have any questions and so forth, anything that we can help you run better and faster on our platforms. So the work is a collaboration, as I said, with NIWA research software engineer, so Yinjing Lin, with whom we work very closely, and also hydrologist Christian Zamit at NIWA. So in that presentation, hopefully you will learn three things. You will learn what a memory leak is, and why memory leaks are sometimes nefarious, sometimes they're fairly harmless, but they can be a big impediment to research. And then we address, we'll talk a little bit about some strategies to plug memory leaks. So the use case, this is a scientific code developed, running at NIWA on a daily basis operationally, so very, very important. And it computes the water flow in rivers. Now that sounds like a very simple thing, but actually it's fairly complex because it involves a lot of processes from anywhere from rain, precipitation to upwelling into soil, to evapotranspiration from plants and absorption of the soil, drainage, and so on and so forth. And this is of course very, very important because, as I will show in the next slide, is that there was an event in 2021 where a river, the Buller River, flooded, and it caused enormous damage. More than 2,000 people had to be evacuated. More than 70 houses were deemed unsafe for habitation, and close to 400 houses needed very substantial repair. So all these processes that you see on the left-hand side have to be combined at the end into a water equation balance equation, and that equation involves, river branches and things like that. And the picture at the bottom sort of shows a little bit the complexity of a river system, a catchment area, with the red areas showing where the river flooded, and the blue ones where it didn't. And now you have to represent, that topography, that topology, I should say, as well as the topography is also very important. And that's a very sort of unstructured kind of approach. You can't use a grid to represent something that looks essentially like a tree. On the top right, you can see exactly what happened, and you might be able to recognize a few cars actually stuck in the mud and trying to completely flooded, with maybe a police car at the back. So that's sort of the environment, or that's sort of the motivation of our work. So we were facing a mystery, and scientist Christian Zammit, had a problem, and he went to us and he said, well, we're running these cases with TopNet for large catchment areas, and it's concerning that the memory requirements becoming very, very large. And then I asked him how large, and he said, well, the biggest one was 900 gigabytes. Now that's a big number by any measure, because TopNet is a serial code, so it's running on one processor. And you normally don't have a machine that has one processor and 1 terabytes of memory attached. So typically what you have to do, you have to take the whole, a whole node of a supercomputer in order to access that much memory. And at NZRSE, we have about 4 of these nodes, not many. And they tend to be used for genomics and other applications, so they're in fairly high demand. But it's very expensive to run a code like that, and so you sacrifice a whole node just for one processor. If you have hundreds of processors on that node, then you have essentially 99 processors, 127 processors completely idle and just one running, just in order to get access to that level of memory. So that was the motivation, and we. So the idea to approach the problem was that NEWA and NZRSE would work together on the problem, and they would use our consultancy service. So we have something in place which allows researchers across New Zealand to get our services most of the time for free. And what we do is, we can work on performance improvements, we can work on data science problems, software sustainability, visualization, or sometimes it's just technical expertise, or just adding another pair of eyes, just looking at the code and see if we can improve something. So if that's something that might interest you, then you may just write down, that email address, support@nzrse.org.nz. And we have a web page. If you Google for it, then you can see examples and case studies where we worked with scientists on improving their workflow or whatever had to be done. So there are a couple of steps that we tend to go through when we face an issue like that. And the first thing is of course confirming the problem, because we like to believe the scientists and so forth. And in fact, initially we didn't see any issue. So, for about 1 week or 2 weeks, there was some back and forth emails going around, and, don't see any issue with the memory. I mean, I was running and, memory was about 5 gigabytes, 10 gigabytes, 8 gigabytes, not the 900. Eventually we were given a case which showed something that we thought could actually be indicative of what was going on. And so we used a tool. Here we use the ARM map tool, which is available on NZRSE platform. And it's a profiler. So what it does is it looks essentially at the performance of the code, but it also provides information about the memory consumption. And that's sort of the graph at the bottom. So it's that red line. And what we can see is that it sort of increases over the length of the simulation. So we made the problem as short as possible, because there was no, we didn't want to waste a terabyte of memory just to see a problem. We want to see the problem, want to make it as small as possible. And so that was sort of interesting, and we thought, okay, well, something is going on here, but maybe it's okay, maybe it's the code is actually meant to do that. But the fact that it was increasing linearly was slightly suspicious. So the next step, what we went through is to zoom into the problem. So we took that same tool, ARM map. And then we took a very, very tiny window where we saw that there was a small jump. And this is very small, and I apologize if it's hard to see on the screen. But at this scale, because this is a zoom view of the trace, horizontally is the time, and vertically is the memory consumption, there's a tiny little jump. And so we thought, okay, let's take a look at that. We created a small little window in our profiler and then looked at all the subroutines and functions that were called in that window. And they were only like 2 or 3. So then the next thing that happened was that I went on holiday and then Yinjing actually found what was called the massive, essentially, memory leak. I mean, hundreds of megabytes, every month or so, which potentially causes, could be responsible for that 1 terabyte requirement that Christian was referring to, particularly because people are running sometimes over many years. And so we then use another tool, which is called Valgrind, which is open source. And Valgrind basically tells you if some parts of the memory are no longer accessible. So if you're allocating some memory and suddenly you forget to deallocate, you quit your subroutine or your function, then essentially that space is allocated, but nobody can actually reach it. And this is the definition of a memory leak. So I'm not going to flood you with a lot of information, no pun intended. But the point here is that we fixed those memory leaks to the point where at the end it was completely clean, right? There was not a single byte lost. So this slide sort of shows the difference between before and after. Before is at the top, and after, again, is a short simulation. We see the increase of the memory before, and then after it's basically constant. The memory requirements are also smaller for that short run. I think was just about 4 gigabytes in before, and then 1.6. So that's good. And I'm ready to talk about to go to the summary at this point. Memory leaks, memory that you can no longer access. Memory leaks can be very costly. They're not often noticeable. When you start developing a code, you don't necessarily see them because the data sets are small, the catchment areas are small. This is applicable to any code, essentially, any code that is using pointers in particular. If you go back to that representation of the river system, you could see all these branches. To represent these branches, you need a linked list, so you have to be very careful in the implementation of the linked list, and you have to be very careful in recovering the memory when you no longer need a branch of your river system. The memory leaks can be hard to track down, so that's why we took 1 or 2 weeks to even realize that we had one. But there are tools that are there to help you. The ARM profiler is not an open source tool, but it's something that is available on NZRSE platform, and you should use it if you have a need for it. Valgrind is also installed on NZRSE platforms, and you can install it on your laptop, Linux. It's basically a Linux system tool. And we recommend that people make a memory leak detection part of their development cycle. So initially, we only had a few nodes out of our big system that were able to accommodate, the simulation. At the end, basically, you can run anywhere. You could even run on a laptop now because the memory requirement is 5 gigabytes or less. In addition, we improved the performance by 40%, up to 40%, depending on the case. That's because if you have, the memory was all segmented, and we also had a performance issue that we fixed, while fixing the memory leak, something that we just stumbled upon coincidentally and improved the I/O. I would say that it's great to have another pair of eyes looking at a code. And we think this is really the role of research software engineers. One way I think we can be useful to organizations is to help different groups and be moved, from one group to the other. Just work for a short time, a few months. In this particular case, I think we probably worked probably less than 3 months. So it's very short time intervention, and it can make a significant difference. So it's also a collaboration, working together with the scientists and having the engineers working together as opposed to in separate group, I think is something that is laudable and we would recommend. That's it. I'm happy to take some questions.
Thank you very much, Alex. That was very interesting, and talking for myself, it's not something that you often think about sometimes when you develop code. I have a first question from Paula, who is asking how likely is that a developer of research software will use a profiler when they are developing the software before it goes into the HPC for broader use?
Well, it's unfortunately the answer is probably fairly low, and it should not be. So I think, Paula, thanks for the question. I think there are so many tools around us that we don't even suspect the existence, even when one is a developer, just because we haven't been exposed or for various other reasons. And what I would recommend in that case, now, obviously, we cannot be exposed to all the experts in every tool. But I think what is very useful in this case is perhaps talking to people and see how they would actually tackle that particular problem and see what they would recommend. That's a good thing. We don't have to sort of work in our own little bubble and try to solve all the problems ourselves. It's perfectly okay to go out, talk to people, and see what's out there and see what they recommend.
That's a very good point. Okay, there's a comment by Hilary who loves the dripping tap painting. And then we have a question from Maxime, who say, nice talk, and asks how easy or not is it to run a program with Valgrind, and also how much impact on the runtime should be expected?
Very good question, Maxime. Excellent question. I forgot to mention that there's a cost involved with running the tools themselves sometimes. And now, in the case of ARM-MAP, that cost was very minimal. So I think it's probably of the order just of a few percent. But Valgrind is a different story. So I might have to reiterate here the need to reduce the size of the problem to its absolute minimum, because what Valgrind does is it intercepts, I think, all the calls to malloc on the system, allocation of memory and things like that, and tries to just write down, how many bytes and in which part of the code the allocation takes place to track these memory leaks. And that, I think it can easily run 10 times slower and possibly even 50 times slower. So that is why it's so important to make these tools maybe part of the software development. So having some unit tests that actually run Valgrind, on some very small, short examples, because once you enter the realm of production simulations and terabytes of data, then it could potentially be too late to make these tools really applicable.
Awesome. And we have time for one last question by Chris, who is asking, is there any initiative at NZRSE to encourage new code to use more memory-safe languages like Julia or Chapel where possible?
Yeah, thanks very much for that question. So some languages don't suffer from the same shortcomings as maybe C and Fortran, and to some extent also C++, because they have pointers and now the thing is, even if you're using Julia, even if you're using Python, you write an extension, and certainly for Python, Julia might be a bit faster, so maybe there's less need for writing extension. But you can have a leak in your extension, and remember that Python is also written in C. So the developers certainly did a great job in avoiding any memory leaks. But if you're writing an extension, be careful.
Thank you very much. So thanks again, Alex. That was very interesting. And we are going to move on to our last speaker for this coming session. So please welcome Paula Martinez, who is a project coordinator at the Australian Research Data Commons. And she's going to give a lightning talk on shaping research software engineering stories. Thank you very much, Paula.
Kia ora to everyone. I'm Paula, and I'm based in Brisbane, Australia. So I would like to start by acknowledging the country in which I live and I work. It's the Turrbal and Yagara's land, and I acknowledge the traditional owners of this land, the elders past and present and emerging leaders. Today I'm going to talk to you about one of the projects that I work in, and it aligns very well to the topic of this conference, empowering communities through research software from innovation to impact. So the Shaping Research Software series that you can find on our website, ardc.edu.au, has a vision that is to ensure research software is recognized as critical national digital research infrastructure. And to be able to come to this vision, we need to make research software more visible and shape for wider reuse. So I'll talk about three benefits that our series bring, and I'll explain with some examples. One of the first benefits is visibility and recognition. So I'd like to introduce you to Lydia and Sam, who are the winners of the new developers of open source software for data analytics. In 2022, they developed a software both as an R package and a Shiny app. And this builds recognition to very new developers. And it also helps them express what they are working on, because it's a bit difficult for research software engineers to explain what they do. And when they talk about it in our interviews, it's in a very common language that everyone, independent from their domain and the level of expertise, can understand. Another benefit for the series is guidance and best practices. So here I'd like to highlight Dr. Juan Núñez Iglesias, whose software, open source software, he developed two tools, Scikit Image and Napari, which accelerate biomedical research and also went to other domains that include breakthroughs in lung cancer detection and deforestation monitoring, and even archaeological artifact description. So by developing software, we are empowering researchers with powerful, reusable solutions that can go from one domain to another. The third benefit of the series is advocacy, and it helps in developing a culture that recognizes and rewards research software outputs. The academic culture needs to start valuing more high-quality, reusable, and maintainable tools, because this accelerates scientific discovery across different fields. So those are the three benefits that the series brings. And I also like to link to one project that goes together with the series, which are the ARDC supported Research Software Awards. So first, I'd like to highlight the Eureka Prizes for Excellence in Research Software. This is a national prize for established research software authors that need to be recognized. And the others that are cited here are collaborations that we made with societies, for example, the Statistical Society of Australia, the Australian Astronomy Society, the Ecological Society of Australia, and the ABACAS, the Australian Bioinformatics and Computing Science Society. And if you see the last four mentioned are for new developers, for emerging leaders, for also outstanding software developers, and I like to highlight the Software Maintainer Award as well. And in taking this series, we also had an implicit approach to growing a community of research software engineers, where we take people to be interviewed, and we also share these stories. And this has collaborated in the growth of this community. Some of you might be part of it already, and if you're not, you can join by going to rsc-aunz.org. And to finalize this lightning talk, I would like to give you a little bit of a taste of the diversity that we have collected with these stories in terms of many disciplines that we work with and the different institutions that are supporting research software engineers. So in disciplines, we go from astronomy to statistics in alphabetical order. You can read them all. And from institutions, we have a lot of universities, from the top 10 universities to smaller universities, government departments, and research institutions. So if you'd like to be part of the series, please get in touch and also read them via our newsletter. We publish them once a month. And to finalize, I would like to invite you all to International Data Week that is coming to Brisbane, Australia in October next year. That's all from me, and probably I have time for one question.
Thank you very much, Paula. That was super interesting, and I completely agree that it's really important to make sure that research software engineers are part of the story. So it's amazing to see the initiative that you've been talking about. Again, we do have time for a couple of questions, so please don't hesitate to put any question that you have for Paula in the live Q&A. But in the meantime, I wanted to start by asking, in the series that you mentioned, so what is the process? How do you choose who gets featured? Like, do you get people who are recommended? Do you find emerging research software developers to talk about? How does that work?
Yeah, we'll try to have recommendations. So we always ask people who read the stories to recommend somebody else. And also another part comes from the winners of the awards that I mentioned before. And they not only have winners, they might have runner-ups or second in line. So we have a lot of people that might be included in the series. And then we approach them and we ask them whether they like to participate. And if they do, we interview them and we publish them with some collaborative edits with the marketing team.
Oh, that's very interesting. And how long has the series been running for?
It's been running since June 2022.
Okay. Oh, so that's good. You had time to feature quite a number of people, I imagine.
Yeah, we have almost once a month, but maybe 10 a year because we don't publish in January. We give them a break.
Sounds good. I do not see any questions currently in the chat, but please feel free to contact Paula if you have any questions. And once again, Paula, thank you very much. That was really interesting. So I would like to finish the session by just thanking again all of the speakers. We had really interesting talks, and I think it's a really good start for the 2 days of the conference. So just a brief reminder before we break out for lunch that we are right now having our lunch break, who will run until around 1:30. So if you can join just before 1:30 for 1:30 p.m. New Zealand time for the next session. And thank you very much again for all the speakers of the sessions.